Anybody think you got the last one?
Yeah, I
reaction?
explained why I want a group grade.
Not that last one.
All right, I wasn't sure.
Good answer though. So if I remember right,
I put Brownstead base, but it's probably wrong.
close.
It's the acid,
No,
then it's the nucleophile, because that's closest to it.
it was something like this, right? And then you went through, and it became. I'm probably missing. Why are you not drawing? You silly device. Oh, I forgot to hit that. There we go. Here, since I'm now back over here. And then it went to that ring. How do you think you should approach it?
I thought the oxygen on the left bond breaks, and if you look at it, how that oxygen is, if you were to flip that chain and then torque this one that way, it would look similar.
The
than you
left
torque-
oxygen broke?
Yeah.
I think the right one, you just, looks like if you just count carbons, you can make that chain work.
So there's a very big first important step when you go through and try and address these kind of problems. Counting carbons. Identifying where your carbons are and trying to find some piece that stands out. I forgot to draw this on here. That hydrogen as well. So we could go through and just compare left to right. Okay? Everything should add up. I'm pretty sure I had this balanced. The one thing that I personally see that jumps out is that carbonyl, the carbon-oxygen double bond. What type of carbonyl is that? I know it's a bit of a stretch, but you guys should be able to do that from first semester. It's not just the carbon-oxygen double bond. Is it an acid? Is it carbonyl from a carboxylic acid? Functional groups? Really? You guys didn't do functional groups?
I don't know which one you're pointing to.
Oh.
Right.
Oxygen on the far right product. This carbonyl. What type of functional group is that?
The
ketone.
Ketone. Okay, good. So it was my fault. I didn't clarify. So we're looking at a ketone. So I can then go back to the starting material and hope that we aren't doing a whole bunch of individual steps. Because ideally what we want to do is find as simple a route as possible. So we go back to our starting material and say, do I have a carbon-oxygen double bond that is also a ketone?
Oh yeah, that one.
Got one right here. So we could then try and evaluate what things changed around that carbonyl. Did anything happen to the CH3 out there? No, it still shows up in the product. What happened to the carbon next to it? What does that carbon have attached to it right now?
Double bond. And the ring.
Oh, you're jumping to the product. Let's look at the starting material first, but yes. If we look at the starting material, what things are attached to that carbon?
CH2.
2 hydrogens and those 2 carbons. If we try and identify that carbon in our product, where is it?
On the right side at the top.
It's the carbon most likely right next to our carbonyl. Think simple first. What happened to that carbon? As we compare across the reaction.
Hydrogen.
Lost 2 hydrogens. So somehow or another in the course of this reaction, these 2 hydrogens must be removed. So the next part of the question said something about adding a base. What do bases tend to react with? Acids, also known as hydrogens. Okay? So that base would potentially remove a hydrogen from that carbon. What charge does that carbon become if it loses a hydrogen? Everybody agree?
Carbocation. Right?
The electrons in that carbon-hydrogen bond, where do they spend most of their time?
Next to the carbon.
Why next to the carbon?
Larger and more electronegative.
Larger is not going to put it closer to the atom, though. What is going to put the electrons closer to the atom? The electronegativity. So when we're going through and evaluating all of the individual chemistries that you saw last semester and this semester, you go back to electronegativity in size a lot. Okay? If there's no difference in size, and it's really hard with hydrogen, but hydrogen is effectively, yeah, it's difficult to compare with hydrogen. We look at electronegativity here. Carbon is slightly more electronegative than hydrogen, which means where do those electrons spend their time? On the carbon. Okay? Let's look at it from a different perspective. We said we were adding a base. What base did we add? KOH. When we look at KOH, what makes it a strong base? What part of KOH is a strong base? The oxygen. Okay, in that structure. So what we can do is actually look at KOH as instead, based on the Lewis structure, and what charge would that oxygen have? Negative. What does that negative need to react with? Something positive. So it's going to react with a positive hydrogen, which means hydrogen comes off as positive. What does that leave on the carbon? Negative. Okay? So what we're trying to do is evaluate where the electrons shift, how they move through the individual structure. And all we're trying to do is go back to our definitions, acids, bases, electronegativity, and apply them to each individual step. If that atom now has extra electrons, what would it most likely act as? An acid or a base? What does an acid need to have? Hydrogen. Well, that carbon does have a hydrogen attached to it. If it acts as an acid, it gives up another hydrogen, right? What charge would that carbon become? -2. Is charge a good thing or a bad thing? How many people have stuck their finger in an electrical outlet? Yeah, was that a good thing or a bad thing? Not particularly a good thing. Why not? What's coming out of the electrical outlet? Charge. Okay. So when we're looking at individual reactions, we want to kind of predict what's happening to the charges. Is it very likely that something that is already charged going to become even more charged? Not such a good option. So having that carbon act as another acid is probably not going to happen right away. So what's the definition of a base? Proton acceptor, reasonable definition. Which base did you just define? Lewis or Bronsted? Bronsted. Why do we not like Bronsted definitions? Very, very narrow. They apply only to the transfer of hydrogen ions. Okay, we can't look to see how that could apply to all chemistry. So what's the other definition? Lewis. Okay. Would this act as a Lewis base? It has extra electrons. What could it do? Could share those electrons with something. If it shares them with a hydrogen, what did it act as? A Bronsted base. If it shares them with an atom other than hydrogen, it's a Lewis base, also known as nucleophile. Okay? If it's a nucleophile, what does it need to react with? Good first answer. What is an electrophile? An electrophile is something that is electron-loving. So it wants to react with electrons. What charge should a nucleophile be? Sorry, an electrophile. Positive. So go back through the rest of the structure. Is there some other atom in our starting material that is positively charged? Do you see a positive with a circle around it? I always draw circles around my charges. The answer should be no to that. No. Okay. Is there an atom somewhere in that structure that could become positive relatively easily? Yeah. What atom? There's two, actually. There's two atoms that could become positively charged relatively quickly within that structure. The oxygen? And you give it to where? Yeah. So what you're starting to do is evaluate the chemistry. What's special about oxygen over all the other atoms in this structure?
Has really
I didn't like that answer, but that is true. It's the most electronegative, which then leads us to the resonance. What does it mean to be more electronegative? What is the definition of electronegativity?
Hard to be
Grabs a hold of not just electrons, bonding electrons. Is there a bond near that oxygen that it could take electrons from? Yes. If it does, what happens? The carbon becomes positively charged. What could I hook up that positive with? How about the negative of that other carbon? Okay. That then folds the structure in on itself. Yes, we still have more steps to go through, but all we're trying to do is evaluate those individual sites of reactivity and start to push reactions on it. Okay? How do we know that we should have started, I know I'm done, with this carbon? Why should we have started with that circled carbon, as opposed to, say, the carbon over here?
Look at the product you have.
Yes, you look at the product. Okay? Compare reactants to products in every situation. Try and find those patterns and simplify. Some cases you aren't given that information, but if we give you that information, take advantage of it. Okay? Use it to your benefit and try and use that to help you filter through it. Okay? So the material that's actually in this problem, at least to the extent that was asked on the quiz, is stuff that you guys should already know. Does it look easy? No, it looks really confusing and hard. That's fine. Okay? Boil it down to the things you should already know. Electronegativity, bring in size. You can start to bring in resonance, but it's a slightly more long distance application. Okay? So break it down into the simplest steps first and try and propagate your way forward. One of the things you'll find, particularly at the tail end of this semester, as I'll stop talking,